Right now, as you sit wherever you are, there is a number quietly ruling the structure of reality that almost nobody ever hears about. It marks a distance so small that if you tried to imagine it, your brain would simply give up. This is the Planck length, a scale where space stops behaving like smooth emptiness and starts acting like something wild and quantum. Our best theories, general relativity and quantum mechanics, both work beautifully, yet they tear apart at this boundary. Tonight we're going to fall all the way down to that edge and watch them fail. Along the way we'll see how your own body, your room, and every familiar object dissolve into something stranger than science fiction. If you enjoy this kind of deep, slow journey into the weird side of physics, remember to like this video and subscribe so you do not miss what comes next. In everyday life, distance feels simple. It is the size of objects around you or the gaps between them. It seems like a smooth line you can chop into as many pieces as you want. If you want to measure a meter more precisely, you imagine cutting it in half, then in half again, and keep going forever. Mathematics is happy with that picture. Physics quietly says no. Reality seems to have drawn a tiny stubborn line in the sand and said no smaller than this. That line is not something we built in a lab, and it is not a technical limit like the sharpness of a camera lens or the resolution of a screen. It comes out of the way the universe itself is wired. When we try to combine the rules that govern gravity with the rules that govern the quantum world, a specific distance falls out of the mathematics. That distance is the Planck length, and it behaves less like a mark on a ruler and more like the pixel size of the universe. The number itself sounds almost meaningless. The Planck length is about 0 point and then 34 more zeros before a 1 of a meter. It is smaller than anything you will ever see, smaller than anything any microscope could ever resolve, smaller than any distance we could hope to probe directly, even in principle. Our best particle accelerators cannot come remotely close to touching it. And yet, according to our current understanding, this absurdly tiny scale is where the real drama of physics begins. To see why, we have to talk about the two great pillars of modern physics. General relativity describes gravity as the curvature of space-time itself, a smooth, flexible fabric that bends and ripples under the influence of mass and energy. It works superbly for planets, stars, galaxies, and the expanding universe. Quantum mechanics governs the world of atoms, electrons, and fields. It says that energy comes in discrete chunks, and that particles behave like smeared-out waves of probability. It explains chemistry, electronics, nuclear reactions, and the structure of matter. Here is the problem. General relativity assumes that space-time is smooth all the way down, with no smallest bump or grain. Quantum mechanics assumes that everything is fundamentally jittery and uncertain. When you push them toward the Planck length, they both demand to be in charge. Their equations start to clash, and the neat answers they give at larger scales turn into infinities and nonsense. The Planck length is the arena where this fight happens, and right now we do not have a referee. One way to picture it is to imagine zooming in on a photograph. From across the room, the image looks smooth and continuous. Move closer, and you start to notice texture and grain. Eventually, the illusion breaks. The picture stops being a landscape. It becomes a grid of square pixels. At that point, talking about a distance smaller than 1 pixel on the screen stops making sense. The Planck length is like that pixel size, but for reality itself. At distances much larger than the Planck length, space-time behaves like a smooth surface. Objects have well-defined trajectories, and waves have clean paths to follow. Gravity curves the fabric gently around stars and galaxies. But if you could somehow zoom in by 35 orders of magnitude down to that Planck scale, we expect the smoothness to shatter. Space-time would no longer look continuous. It would break into unpredictable quantum fluctuations, a restless pattern often described as quantum foam. Nobody has ever seen the Planck length directly. We have no microscope that can resolve it, no instrument that can poke space-time at that scale and report back. Yet the Planck length is not an arbitrary guess or a random number that looked elegant on paper. It arises from constants that we have measured with exquisite care. The speed of light which ties together space and time, Newton's gravitational constant which sets the strength of gravity, and Planck's constant, the tiny number that measures how grainy the quantum world is. Combine these three constants in the right way, and you get a length, a time, a mass, and an energy. Each one marks a boundary where our current theories cannot be trusted. So when physicists say there might be a smallest distance, They do not mean there is an invisible wall in space that you bounce off like a force field. They mean that nature itself might not recognize distances smaller than that. Ask the universe to give you a measurement below the Planck length, and it may simply refuse to answer in any meaningful way. Space could stop being a stage where events happen, and instead become a derived concept, something that emerges only when you zoom out far enough. In the rest of this documentary, we're going to walk steadily down through the scales toward that edge. We will start with the size of your own body, then move down to cells, molecules, atoms, and the particles that make up atoms. We will see how each step required new instruments and new ideas, and how each step brought us closer to the point where our current theories tear open. By the time we reach the Planck length, you will see why many physicists think of it not as just another small number, but as the place where reality itself changes character. Before we dive straight into Planck scale weirdness, we need to appreciate how hard the universe has made us work just to see a tiny bit beyond our own senses. For most of human history, the smallest things you could reliably talk about were things you could touch. Grains of sand, specks of dust, maybe the faint blur of a gnat hovering in the air. The idea that beneath those familiar specks lurked entire hidden worlds would have sounded mystical rather than scientific. The first great step was not a machine, it was an argument. In ancient Greece, philosophers like Democritus suggested that matter might be made of tiny indivisible units, which he called atoms. Others, like Aristotle, insisted that matter was continuous, that you could keep cutting it forever and never hit a hard limit. No one had a microscope. No one had a way to test either idea. So the question of whether the world was granular or smooth became a matter of taste and philosophy rather than experiment. For almost 2,000 years, that is where the debate stayed. People tried to reason their way to an answer using logic alone. Nature, meanwhile, stayed quiet. It did not care which story humans preferred. It simply kept its tiny structures hidden behind a wall our eyes could not cross. Then, in the early modern period, humans finally built tools sharp enough to start scratching at that wall. Simple glass lenses, polished by hand, turned into magnifying glasses and early microscopes. At first they were crude. They made things bigger, but also blurrier and distorted. Even so, they showed something shocking. The little fuzz on the surface of a leaf was not fuzz at all. It was forests of tiny structures. The skin of an insect became alien armor. A raindrop turned into a miniature lens filled with strange patterns. As microscopes improved, a new layer of reality came into view. Cells, bacteria, tiny creatures swimming in a single drop of pond water. The invisible world was suddenly populated. You could now point to a thing no one had seen before and say, look, there it is. This was the first time the idea of invisible structure stopped being philosophy and became something you could literally see with your own eyes, aided by some glass and patience. Even then, the atomic idea remained in limbo. You could see cells, but you could not see atoms. Chemistry stepped in to push us further. In the 19th century, scientists noticed that elements combined in fixed mass ratios. Water always contained a specific proportion of hydrogen and oxygen. These patterns made sense if elements were made of discrete chunks that hooked together in whole number counts, the way Lego bricks snap into specific combinations. The atomic theory began to harden into something more than a metaphor. Still, no one had actually watched an atom. There was a lingering worry that the whole picture might be a clever accounting trick that just happened to work. Then came a deceptively simple observation that tipped the scales. Put a tiny grain of pollen in water and look at it through a microscope. Even when the water is still, the grain jitters and dances randomly. This is Brownian motion. Einstein showed that this jitter could be explained if the pollen was being bombarded by countless invisible molecules. The random hits added up to visible wiggles. If those molecules did not exist, the motion made no sense. Suddenly, atoms were not just a neat way to label chemical recipes. They were real, measurable players in physical phenomena. By this point, our instruments and our equations had built a bridge from the human scale down to molecules of water and oxygen and carbon. Microscopes revealed structures as small as micrometers, millionths of a meter. Later, with electron microscopes, we pushed to nanometers, billionths of a meter, seeing viruses and large molecules as ghostly outlines. With each improvement, the world became stranger and more crowded. Surfaces that seemed smooth turned out to be folded landscapes. Empty air became a swarm of invisible particles in constant motion. But even an electron microscope cannot show you an atom the way you might imagine it. Atoms are smaller than the wavelengths of visible light. To see them, you have to do something more radical than building a better glass lens. You have to turn to particles as probes. You accelerate electrons to high energies and fire them at your target. Their wavelengths shrink as their energy rises. Then you use their scattering pattern to reconstruct the structure inside. The microscope turns into a kind of giant quantum radar. This is where the story of seeing the invisible merges with the story of smashing. Particle accelerators are essentially machines that fling probes at matter with ever-increasing energy, then study the debris. At first, they revealed electrons orbiting tiny dense nuclei. Then they uncovered protons and neutrons inside those nuclei. Pushed to higher energies, and protons themselves showed inner structure. Quarks, gluons. The protons stopped looking like a billiard ball and started looking like a buzzing cloud of fields and excitations. Crucially, at each stage we used the same basic trick. To see smaller structures, we needed probes with shorter wavelengths, which meant higher energies. More energy focused into a smaller space gives us finer resolution. It is like switching from a blurry low-resolution camera to an ultra-sharp one, except the pixels here are waves of matter and light slamming into your sample at near light speed. By the late 20th century, this strategy had taken us to astonishing extremes. We had measured distances down to around 10 to the minus 18 meters in scattering experiments. That is a billionth of a meter. At those scales, electrons and quarks look point-like. No internal structure shows up in the data. To our best measurements, they behave as if they have no size at all. So you might be tempted to draw a clean line. Microscopes see cells and bacteria. Electron microscopes see viruses and molecular shapes. Particle accelerators reveal atoms, nuclei, and then quarks and electrons. End of story. We just keep building bigger machines, pushing to higher energies, and the universe keeps handing us smaller building blocks. But that neat pattern hides a looming problem. There is nothing in this simple story that warns you there might be a limit. It suggests you can always pay more energy to buy more resolution. The Planck length quietly disagrees. When we try to follow the logic of higher energy equals finer resolution all the way down, general relativity and quantum mechanics team up to stop us. At some point, the very act of concentrating enough energy into a small region creates so much gravity that space-time itself collapses into a tiny black hole. Your probe stops being a helpful particle and turns into a gravitational trap that hides whatever you were trying to see. That is the wall we are heading toward. Our journey from grains of sand to quarks and electrons was a triumph of technology and imagination. It taught us that reality is layered and that our senses are only the first crude instruments. But it also set us on a collision course with the fundamental structure of space-time. In the next part, we will walk into the heart of the atom itself and see how the idea of size becomes slippery long before we ever reach the Planck scale. Up to this point, our journey has moved steadily downward, from the human scale to cells to molecules to atoms. Each step has felt like pulling back another curtain to reveal smaller pieces like nesting dolls. It is tempting to assume this pattern just keeps going. Atoms are made of smaller parts. Those parts are made of even smaller parts. The staircase continues forever. That picture is comforting because it is familiar. But once you step into the atom, the rules quietly change. The idea of size starts to slip through your fingers. The story begins with a thin sheet of gold and a source of particles. In the early 20th century, Ernest Rutherford and his team fired alpha particles at gold foil. At the time, many physicists pictured the atom as a kind of pudding, with positive charge smeared out and electrons embedded inside like raisins. If that were true, the incoming particles should slip through with only gentle nudges. That is not what happened. Most particles did pass straight through, but a tiny fraction bounced back at sharp angles, as if they had slammed into something small and very dense. Rutherford famously said it was as surprising as firing a cannon shell at a sheet of tissue paper and having it bounce back. The only way to make sense of the data was to imagine almost all of the atom's mass concentrated in a tiny central nucleus, with electrons orbiting far away compared to its size. This was the first hint that atoms are mostly empty space, and that the things we touch are not solid in the way we think. If an atom were the size of a stadium, the nucleus would be a grain of rice in the middle, and the electrons would be ghostly smears buzzing near the outer walls. The chair you're sitting on is almost entirely vacuum, held together by electrical forces and quantum rules. As experiments progressed, the nucleus itself refused to stay simple. It turned out to be made of protons and neutrons. For a while, people hoped that might be the end of the story. Electrons on the outside, protons and neutrons at the core, job done. Then the next generation of accelerators started slamming particles together at higher energies, and the debris told a different tale. Protons and neutrons did not behave like featureless marbles. When you smashed them hard enough, they shattered into smaller constituents that behaved as if they were trapped inside. These new players were named quarks. Gluons emerged as the carriers of the strong nuclear force that binds quarks together. Instead of solid balls, protons and neutrons looked more like seething clouds of quarks and gluons, constantly exchanging momentum in a dynamic dance. So once again, the nesting doll picture seemed to hold. Atoms contain nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons contain quarks and gluons. It feels natural to ask what quarks are made of. But here the quantum world pushes back in a different way. When we say we have measured the size of something in a scattering experiment, what we really mean is that we have looked for signs of internal structure. If the probe particles bounce off in a way that suggests a smooth object, we call it point-like down to that resolution. If the scattering pattern starts to show substructure, we say we have resolved a finite size. Electrons and quarks, as far as we can tell, keep behaving as point-like objects all the way down to the smallest distances we can probe. There is another twist. In classical physics, you can imagine a particle with a definite position and a definite size, like a tiny hard sphere. In quantum mechanics, that image breaks. Particles are described by wave functions, which spread out through space. The wave function tells you the probabilities for finding the particle in different places if you measure it. Until you do, the particle does not sit at one sharp location. It is smeared out. So when you ask how big an electron is, the quantum answer is slippery. You can talk about its effective size in terms of the region where its wave function has significant weight. You can talk about a classical radius defined by how strong its electric field is. You can talk about its behavior in scattering experiments. Each definition gives you a different notion of size, and none of them match the simple picture of a tiny ball. Then there is the uncertainty principle, quietly sabotaging our attempts to pin things down. The more precisely you try to localize a particle in space, the less precisely you can know its momentum. This is not a flaw in your instruments. It is a built-in feature of quantum reality. If you squeeze the wave function into a very narrow region, the spread in possible momenta grows. The particle stops behaving like a well-behaved dot and starts behaving like a wild distribution of possibilities. You can think of it this way. To see something small, you need light or particles with very short wavelengths, which means high energies. But high-energy probes disturb the thing you are trying to observe. At some point, the very act of looking fundamentally changes its state. The particle you're measuring is no longer the same particle you set out to describe. In the atomic world, this trade-off shows up in everyday phenomena. Electrons in atoms do not orbit the nucleus like little planets. They sit in standing wave patterns called orbitals, each with a specific energy. You cannot draw a neat track for an electron around the nucleus. You can only draw regions where it is more or less likely to show up if you measure it. The shapes of these regions explain the structure of the periodic table, the way atoms bond, the color of materials, the stability of matter. At nuclear scales, quarks face an even stranger fate. The strong force, which holds them together, grows stronger as you try to pull them apart. It is like a rubber band that resists more the farther you stretch it. Try to separate a quark from its partners, and you pump so much energy into the field between them that it snaps, creating new quark pairs instead of letting one escape alone. This property, called confinement, means you never see isolated quarks in nature. They're always locked inside composite particles. So we arrive at a peculiar situation. The deeper we go into matter, the more our intuitive idea of size falls apart. Electrons and quarks look point-like to our experiments, but their quantum descriptions are smeared wave functions. Their positions and momenta cannot be simultaneously sharp. Some of them, like quarks, are forever confined in bound states we can never peel apart. The classical picture of little solid beads arranged in neat hierarchies loses its grip. And yet, all of this quantum fuzziness still lives comfortably on a smooth background of space-time. We imagine these wave functions spread out over a continuous grid of positions, like mist in a perfectly smooth room. The coordinates we assign are still drawn from a continuous line of possible values. There is no obvious hint in the mathematics of atoms, nuclei, or quarks that there should be a smallest meaningful distance. That silence is deceptive. The quantum world inside the atom is already telling us that nature happily abandons our everyday intuitions when it needs to. Objects are not truly solid. Positions are not truly sharp. Size is not a simple geometric property. Once we accept that, it becomes easier to imagine that space itself might refuse to be perfectly smooth. In the next part, we'll see what happens when we try to use all this quantum machinery to measure smaller and smaller distances, and how gravity crashes into the story in a way that forces the universe to draw a line. By now, a pattern might feel familiar. To see smaller things, we use higher energy probes with shorter wavelengths. First glass lenses, then electrons, then particle beams in giant rings. Every time we invest more energy, the universe rewards us with finer detail. At least that is the story we like to tell. If that story were the whole truth, there would be no reason to suspect a smallest distance. We would simply keep turning up the energy knob and zooming in forever. The deeper truth is more unsettling. At some point, turning up that knob does not just illuminate your target, it starts to tear space-time itself apart. To understand why, we need to connect two ideas that usually live in separate mental rooms. The first is the uncertainty principle. In ordinary language, it says this: the more precisely you try to pin down where something is, the less precisely you can know how it is moving. If you insist on squeezing a particle into a tiny region of space, you're forced to accept a large spread in its momentum. That spread means the particle can carry very high energies with some probability. The second idea is the gravitational effect of energy. General relativity tells us that gravity is not just about mass. Energy in any form curves space-time. Light, radiation, kinetic energy, all of it contributes. Put enough energy into a sufficiently small region, and you do not just have a dense object, you have a black hole. There is a critical radius, a boundary from which not even light can escape. Compress the energy inside that radius and gravity wins. The region becomes a one-way trap. Now imagine you're an ambitious physicist determined to measure a very tiny distance, smaller than anything anyone has ever probed before. You build the most powerful accelerator in the universe. You plan to fire particles at each other and use the collision to resolve structures at that scale. To do this, you need probes with wavelengths shorter than the distance you're chasing. Shorter wavelength means higher energy. The uncertainty principle nods in agreement. There is no other way. You focus that energy into an incredibly small region, trying to confine your probe there so it can interact with whatever you're examining. As you crank up the energy, the effective wavelength of your probe shrinks. Your resolving power improves. For a while, everything works as planned. This is the part of the story we have already used to explore atoms, nuclei, and quarks. But keep turning the dial. With each step, you're stuffing more and more energy into a smaller and smaller volume. General relativity quietly raises a hand. At some point, the energy density becomes so high that the space-time around your experiment curves strongly. The gravitational field of your own probe is no longer negligible. It starts to pull on itself. There is a tipping point. Once the energy is concentrated inside a region smaller than the radius of a black hole with that energy, space-time pinches off. You do not get a sharper image. You get an event horizon. The region you hope to study disappears behind a gravitational curtain. Instead of revealing smaller structures, your attempt to measure them has created an object larger than the thing you were trying to see. This is the central paradox. The very method that worked so well for a century becomes self-defeating. Pushing to higher energies to see smaller scales eventually destroys your ability to see anything at all. You cannot simply ignore gravity at this extreme, because your measurement device is now heavy in the most literal sense. Its energy warps the stage it is sitting on. If you run the numbers using the constants we already know, this tension between quantum uncertainty and gravitational collapse becomes sharp at the Planck length. Try to localize something in a region smaller than this distance, and the uncertainty and momentum becomes so large that the associated energy forces the region to become a microscopic black hole. The would-be probe takes itself and the target out of view. The Planck length is where your rulers melt into horizons. This is why physicists talk about the Planck scale as a limit in principle, not just in practice. It is not that our current technology is too weak. You could imagine a civilization far beyond our own, with accelerators the size of galaxies, capable of reaching energies trillions of times higher than anything on Earth. The problem would remain. The laws of physics, as we understand them, say that past a certain point, more energy does not buy you more detail. It buys you gravitational collapse. So what does it really mean to say there is a smallest meaningful distance? It does not mean that space suddenly becomes made of tiny cubes, or that you bump into a hard wall if you try to go smaller. It means that any attempt to define distances below that scale using physical measurements runs into a contradiction. The very act of defining such a distance requires energies that erase the notion of distance in that region. You can imagine the Planck length as sitting at the crossroads of three tendencies. Quantum mechanics wants things to be fuzzy, so that sharply defining a position comes with a penalty in momentum. Relativity ties energy to curvature, so that concentrated energy bends spacetime. Gravity sets a conversion rate between mass, energy, and the size of black holes. When you juggle all three together, the Planck scale pops out as the point where the juggling act fails. There is a deeper lesson hiding here. When we picture measuring devices, we often imagine them as external tools that do not disturb the system much. A ruler does not change the length of a table. A thermometer does not usually change the weather. At the highest energies and smallest scales that separation collapses, the cosmic microscope is made from the same spacetime it is trying to resolve, and its attempt to look closer changes that spacetime in violent ways. This is why so many attempts to build a theory of quantum gravity take the Planck scale as their starting point. It is not just a curious number, it is where the clash between our two great theories becomes impossible to ignore. Below that length, the idea of using ordinary spacetime coordinates to describe physics may no longer make sense. Distances and durations might have to be replaced by something more abstract, perhaps algebraic structures or networks of relations. From our perspective today, this situation is both frustrating and thrilling. Frustrating because it tells us there is a built-in fog that we cannot burn away with more powerful beams. Thrilling because it strongly suggests that there is a new layer of physics waiting to be discovered. Somewhere beyond this wall, there must be a framework in which the formation of tiny black holes during measurement is not a disaster, but a natural part of the story. In the next part, we will look at how a simple combination of three constants of nature leads directly to this boundary scale. We will see how, long before anyone dreamed of gigantic accelerators, the universe had already written the Planck units into its operating manual, waiting for us to notice. Up to now, the Planck length has appeared in our story as a kind of warning sign. Try to look below this distance, and your measuring device collapses into a black hole. That is a dramatic image, but it raises a quiet question. Why this distance and not some other? Why not 10 times smaller or 1,000,000 times larger? The answer is one of the strangest things in physics. The Planck scale falls out of the universe almost by itself, once you pay attention to three numbers that keep showing up in completely different parts of nature. Those three numbers are the speed of light, Newton's gravitational constant and Planck's constant from quantum mechanics. Each one arrived in science through its own long, messy story. None of them was invented to talk about smallest distances, yet together they form a kind of recipe that defines the Planck length, the Planck time, the Planck mass, and other natural units. It is as if the universe hid its own preferred yardstick in a combination lock made of three dials, and we slowly learned how to read them. The speed of light came first, at least in spirit. When Maxwell wrote down the equations of electromagnetism, he found that they predicted waves that travel through empty space with a particular speed. When people measured the speed of light, it matched that prediction. Later, Einstein realized this value was not just about light, it was the fundamental speed of cause and effect in the universe, the fastest that any influence can travel. It ties space and time together into space-time. Newton's gravitational constant is more humble in appearance. It is the number that sets the strength of gravity in the law that tells you how strongly two masses pull on each other. It is incredibly small in everyday units, which is why gravity between small objects is so feeble compared to electric forces. But that smallness is deceptive. The constant is really telling us how mass and energy curve spacetime in general relativity. It is the conversion factor between energy content and the bending of the cosmic fabric. Planck's constant arrived last, and it came from a puzzle about how hot objects glow. Max Planck was trying to explain the spectrum of light emitted by a perfect black body, and classical physics kept giving nonsense answers. To fix the problem, He made a bold move. He assumed that energy could only be emitted and absorbed in discrete chunks, proportional to the frequency of the light. The constant of proportionality is now called Planck's constant. It measures how grainy the quantum world is. Smaller values would make quantum effects weaker. Larger values would make them more obvious. On their own, each of these constants is just a number with units attached. One tells you how many meters of space a light beam crosses each second. One tells you how strong gravity is for a given mass and distance. One ties energy to frequency in the quantum world. The surprising leap is realizing that you can turn these three numbers into units of measurement that no longer depend on any human-made standards. In school, you are taught that the meter and the second are basic units. Historically, the meter was tied to the size of the Earth, and then to a metal bar in a vault. The second was based on the rotation of the planet, then on vibrations of atoms. There is nothing fundamental about these choices. They are convenient, not cosmic. Planck asked a different question. What if we defined units using only constants that seem to belong to nature itself? Units that any civilization, anywhere in the universe, could in principle reconstruct from physics alone. Using dimensional analysis, you can treat the constants like building blocks. The speed of a light connects space and time. Newton's constant connects mass, length, and time. Planck's constant connects energy, frequency, and time. Mix them in just the right powers, and all the messy units cancel out, leaving you with pure length, pure time, or pure mass. The resulting numbers are what we call the Planck length, Planck time, and Planck mass. The values you get are extreme. The Planck length is about 1.6 times 10 to the minus 35 meters, which we can think of as roughly 10 to the minus 35 meters for our purposes. The Planck time is the time light takes to travel that distance, around 10 to the minus 44 seconds. The Planck mass is about 22 micrograms, roughly the mass of a small grain of dust. The corresponding Planck energy and Planck temperature are unimaginably high by everyday standards. Here is the weird part. The Planck length is absurdly tiny compared to the size of atoms, yet the Planck mass is huge compared to the mass of a proton. A proton is about 1 billion times lighter than the Planck mass. That mismatch is not an error. It is a sign that something special happens when you pack Planck mass energy into Planck length volumes. That is precisely where our earlier argument about measurements creating black holes kicks in. You can phrase the Planck length in another way. It is roughly the scale at which the quantum fuzziness of a particle and the gravitational radius of its energy content become comparable. Try to make a particle lighter than the Planck mass, and its quantum wavelength is large compared to its gravitational pull. Try to make it much heavier, and its own gravity threatens to hide it behind a horizon. The Planck scale is where these tendencies balance. It is where quantum mechanics and gravity have equal say. There is something almost eerie about the fact that this scale appears from pure thought. You do not have to build a device that reaches Planck energies to know the number. You only have to measure the constants that already show up in electromagnetism, gravity, and quantum mechanics, and then combine them. In that sense, the Planck units are like a watermark in the structure of our current theories, a hint of a deeper layer beneath them. You might wonder whether this is just mathematical numerology, a game of multiplying and dividing constants until you get strange numbers. Physicists are wary of that temptation, but in this case, the Planck units are not arbitrary. They keep showing up in independent arguments about when our theories break down. The smallest meaningful distance from the black hole thought experiment, the shortest meaningful time interval, the energy at which quantum field theory of gravity stops behaving, all land near the Planck scale. Different roads, same destination. Planck's original motivation was not to predict a smallest distance. He was trying to understand heat radiation and stumbled onto the first quantum. Yet with hindsight, his units now look like the natural coordinates for a theory in which gravity is quantized. In Planck units, many fundamental equations become cleaner. The constants we're used to carrying around as separate characters disappear into the definition of the units. They become ones. What remains are pure relationships between dimensionless quantities. It is as if we have stripped away the human clothes from the equations and are staring at their bare structure. For us, living at human scales, the Planck units can feel comically far away. The Planck time is so short that there have been more Planck time intervals since the Big Bang than there are atoms in the observable universe. The Planck length is so tiny that you could line up more of them across a single proton than there are protons across the visible universe. Numbers like that can numb the mind, but they are not meant to impress us. They are telling us where our familiar descriptions stop being reliable. This is why many physicists believe that whatever theory eventually unifies quantum mechanics and general relativity will look most natural when written in Planck units. At that point, the Planck length and Planck time would not be decorations. They would be the native grid spacing of reality, the fundamental tick marks on an underlying structure that spacetime emerges from. So far, we have talked about Planck units as a kind of signpost, pointing to a territory we cannot yet map. In the next part, we will confront the mapmakers directly. We will see how attempts to quantize gravity in the same way we quantize the other forces run into deep trouble, and why this has driven theorists to some of the wildest ideas in modern physics. By now you have seen how the Planck scale slips out of the constants of nature, as if the universe is quietly warning us that our favourite equations are living on borrowed time. The obvious next move is to do what worked so well for the other forces. We took electromagnetism, the weak force, the strong force, and wrapped them in the language of quantum field theory. It was messy, but it worked. Those theories make predictions that match experiments with absurd precision. So why not just do the same for gravity and be done? Because when you try, Einstein's beautiful theory turns into a stubborn rebel that refuses to fit into the quantum mold. Quantum field theory, in loose terms, treats particles as ripples in underlying fields that fill all of space. The electromagnetic field is one example. Photons are little wave packets of that field. The mathematics lets you add up all the different ways particles can interact, often visualized as branching diagrams of particles colliding, splitting, and rejoining. At first glance, this is a recipe for disaster. Many of these contributions give you infinite answers, but there is a trick. For the electromagnetic force and the nuclear forces, those infinities can be tamed through a process called renormalization. Renormalization sounds arcane, but the idea is surprisingly down to earth. When you zoom in on a particle with higher energy probes, you see not just the bare particle, but a cloud of virtual activity around it. The vacuum is not empty. It seethes with short-lived particle pairs that appear and disappear. These fluctuations shift the effective charge and mass of the particle depending on the scale at which you probe it. Renormalization is the art of absorbing the infinities from these fluctuations into redefined physical quantities like mass and charge, so that the final predictions for real experiments come out finite and well-behaved. The reason this works at all is that for the forces we know how to quantize, the messy high-energy behavior can be captured with a small number of adjustable parameters. Once you measure those in a few experiments, the theory can predict everything else. In this sense, the infinities are like bookkeeping issues rather than signs that the whole framework is broken. The standard model of particle physics, which combines the electromagnetic weak and strong forces, is built on this foundation. It is astonishingly successful. Now bring gravity into this picture. You take general relativity, which describes gravity as the curvature of space-time, and you try to treat the gravitational field like any other quantum field. You imagine tiny ripples in space-time, gravitons, playing the role photons play for light. You draw interaction diagrams, you write down integrals, and you start to add up the contributions. At low energies, this actually works pretty well. Gravity is so weak between particles that the first few corrections are tiny. You can treat quantum gravity as an effective field theory that works as long as you stay far below the Planck energy. The trouble starts when you push the calculations to higher and higher energies, which is exactly what you need to do if you want a fundamental theory that works all the way down to the smallest distances. The infinities that appear in quantum gravity are not the tame kind. They grow in such a way that each new level of correction introduces new types of divergence that cannot be absorbed into a small set of physical constants. You would need an infinite number of independent parameters to cancel all the infinities. The theory loses predictive power. This is what physicists mean when they say gravity is non-renormalizable in the usual sense. There is a useful analogy. Imagine trying to write a simple recipe for bread. A sensible recipe has a handful of ingredients and instructions. You can tweak the quantities a little and still get bread. A non-renormalizable theory is like a recipe where every tiny change in oven temperature, air humidity, or table height requires you to add a whole new page of corrections to keep the loaf from collapsing. At some point, you no longer have a useful recipe. You have an endless list of excuses. This breakdown tells us something profound. General relativity is an incredibly accurate description of gravity at large scales, from planets to galaxies to the whole observable universe. Quantum field theory is an incredibly accurate framework for the other forces at small scales. But if you insist on forcing gravity into the same quantum field box and expect it to behave all the way up to the Planck energy, the mathematics revolts. The two pillars cannot simply be stacked on top of each other. There is mortar missing between them. You might ask whether we can just shrug and say that gravity is classical and everything else is quantum. Maybe space-time is a smooth stage, and only the actors on it are quantized. That line of thought runs into trouble quickly. Quantum matter curves space-time. A particle in a superposition of positions should, in principle, create a superposition of gravitational fields. If the matter is quantum but the geometry it lives in is not, the whole system becomes inconsistent. Most physicists take this as a strong hint that gravity itself must have a quantum description. We just do not know what it is yet. There have been heroic attempts to quantize gravity directly, treating it as just another field and hoping for a hidden structure that restores predictability. Some progress has been made in understanding gravity as an effective theory that works well below the Planck scale, with corrections that can be computed order by order. This is useful for certain calculations, for example in cosmology, or in the behavior of black holes at energies that are high but not truly Planckian. Yet the underlying problem remains. At the deepest level, the theory asks for more input data than we can ever supply. This is why the Planck scale keeps looming over the conversation. As you run the quantum gravity calculation toward higher energies, the non-renormalizable behavior sharpens. Around the Planck energy, the approximations that let you treat spacetime as a gently curved background break down. Quantum fluctuations of the geometry itself become violent. The field you are trying to quantize becomes the arena in which the quantization is defined. The usual tools of quantum field theory, which assume a fixed spacetime backdrop, are being asked to soar off the branch they are sitting on. Seen in that light, the failure to quantize gravity in the straightforward way is not an embarrassment. It is a clue. It tells us that spacetime cannot be fundamental in the way electric and magnetic fields are. Instead, spacetime may be an emergent structure, like the surface of a liquid that looks smooth from afar but is made of molecules churning underneath. Quantum gravity, whatever form it takes, will likely describe those underlying degrees of freedom, rather than just attaching quanta to the classical Einstein field. This realization has driven theorists toward more radical ideas. Some have tried to soften gravity's high-energy behavior by replacing point particles with extended objects, like tiny strings, so that interactions are smeared out over a finite length. Others have tried to quantize geometry itself, turning areas and volumes into discrete spectra. These are not wild guesses thrown against a wall. They are carefully built responses to the specific ways in which naive quantum gravity fails. In the next part, we will follow one of those paths in more detail. We will look at string theory, a framework in which the Planck length becomes the natural size of the fundamental vibrating loops that replace point particles, and where gravity appears not as an add-on, but as a necessary part of the music those strings can play. Imagine you could zoom all the way down to the Planck length and watch reality from there. In the usual picture of particle physics, you would expect to see little points buzzing around, featureless dots whose only properties are numbers. String theory proposes a very different view. At that extreme zoom, the dots stretch into tiny loops and segments. They are not static either. They vibrate, and the claim is bold. Every particle you know, from electrons to quarks to the graviton that carries gravity, is just a different musical note played on the same fundamental string. The core idea is deceptively simple. Instead of treating particles as points with no size, string theory treats them as one-dimensional objects, with a length roughly on the order of the Planck length. That extended nature matters. When strings interact, they merge and split smoothly, like strands of spaghetti weaving together and pulling apart. Collisions are no longer sharp point hits that produce violent infinities at zero separation. The interaction is smeared over the length of the string, softening the worst ultraviolet behaviors that wrecked quantum gravity in the point particle picture. Each string vibrates in many possible ways. You can think of these as different modes on a violin string. Some vibrational patterns correspond to particles with one mass and one spin. Others correspond to different masses and spins. In this picture, an electron is not a special kind of object with intrinsic properties. It is one particular way a string can vibrate. A photon is another. Most important, one of the allowed vibrational modes looks exactly like a massless spin 2 particle. That is the kind of particle you expect if gravity is mediated by gravitons. This is one of the reasons string theory attracted so much excitement. Gravity is not bolted on as an afterthought. It emerges automatically from the mathematics once you accept the premise of strings. Instead of wrestling with a non-renormalizable quantum field for gravity, you get a built-in candidate for quantum gravity as part of a bigger framework. The same structure that explains electromagnetic and nuclear forces in terms of string vibrations has, tucked inside it, the ingredients of Einstein's curved space-time. Of course, there is a price. Strings do not behave nicely in a universe like the one we first wrote down for general relativity. The equations insist on more dimensions of space than the 3 you move through. Depending on the version of the theory, you get 9 or 10 spatial dimensions and 1 time dimension. At first, this sounds like a fatal blow. We do not see extra dimensions when we walk down the street or launch satellites. Yet there is a loophole. Those extra dimensions can be compact, curled up on scales far smaller than an atom, so small that our experiments have never probed them directly. Picture a garden hose from far away. It looks like a simple line. Walk up close, and you see that it has a circular cross-section. There is a surface you can move around. In a similar way, a piece of space can have tiny curled directions you only notice if you are small enough or energetic enough. In string theory, the extra dimensions are not simple circles. They are intricate shapes called Calabi-Yau manifolds, with complex folds and tunnels. A string can vibrate not only along the large dimensions we see, but also wrap and oscillate around these hidden directions. Here the plot thickens. The detailed shape of the compact space affects which vibrational modes are possible, which in turn determines the spectrum of particles and forces in the large 3-dimensional world. Change the geometry of the extra dimensions and you change the apparent laws of physics. Different shapes produce different particle families, different force strengths, different cosmological constants. In principle, this could be wonderful. Maybe there is one special shape that reproduces exactly the standard model in our observed universe. In practice, the situation is far messier. Mathematicians and physicists discovered an enormous number of possible shapes and configurations that string theory seems to allow. The estimates go into mind-bending territory. You can get a landscape of plausible vacuum states, each with its own effective physics. That leads to a troubling question. If the theory has so many possible versions of reality, how do we pick the one that corresponds to our world? Are there deep principles that single it out? Or do we live in one bubble out of many, selected by cosmic history or even by selection effects linked to the existence of observers like us? This is often called the landscape problem. It has pushed some thinkers toward anthropic arguments, where the properties of our universe are explained partly by the requirement that stable matter and long-lived stars exist at all. That direction makes some people uneasy, because it feels less like the sharp predictive power we're used to in physics, and more like a story about where we happen to find ourselves. Others argue that this is simply what a mature theory looks like when it connects to cosmology, and that our discomfort is a sign we are leaving the comfort zone of older ideas. String theory brings other surprises. It does not just describe strings, it naturally includes higher dimensional objects called branes, short for membranes. These can have various dimensions from 0-dimensional points up to extended sheets. In some scenarios, our entire observable universe could be a 3-dimensional brane floating in a higher dimensional bulk, with strings anchored to it. Standard model particles would be vibrations stuck on this brane, while gravity, carried by closed loops of string, could wander into the bulk. This picture gives one possible explanation for why gravity is so weak compared to other forces. It may be leaking into directions we do not see. Another remarkable feature of string theory is the web of dualities connecting different descriptions. Two theories that look completely different at first glance can turn out to be equivalent when viewed through the right mathematical lens. Strong coupling in one description maps to weak coupling in another. A small compact dimension in one picture can correspond to a large one in another. These dualities suggest that the theory is not a collection of separate models, but facets of a single underlying structure we do not yet fully grasp. For our purposes, the key point is this. In string theory, the Planck length is not just a mysterious scale where our equations fail, it is roughly the size of the fundamental string itself. The theory takes the warning from quantum gravity and hardens it into a physical object. Below that length, the concept of a point particle stops making sense because there are no point particles. there are only extended strings and branes. Yet for all its elegance, string theory faces a hard reality test. We have not yet found a clear experimental signature that singles it out. The Planck scale at which strings reveal their extended nature is far beyond the reach of our colliders. Some hoped that hints might show up as supersymmetric partner particles or subtle imprints in cosmological data, but so far nature has been quiet. The theory has produced deep insights into mathematics and black hole physics, and it has given us tools like holographic dualities that are useful well beyond string theory itself. Still, as a description of the world, it remains a proposal awaiting decisive evidence. So we are left with an intriguing situation. String theory shows that it is mathematically possible to have a quantum theory where gravity is built in, interactions remain well behaved at high energies, and the Planck length takes on a concrete role. It gives us a glimpse of how space-time might emerge from something more fundamental, involving vibrating extended objects in higher dimensions. But it is not the only game in town. In the next part, we will explore a very different idea, one that does not add new kinds of matter at all. Instead, it bites the bullet and tries to quantize space-time itself, turning geometry into a network of discrete loops. When people first tried to quantize gravity, most efforts started from the same picture you carry in your head. Space is a smooth arena, a continuous fabric that can bend and ripple, and you sprinkle quantum fields on top of it. String theory bends that picture by replacing point particles with tiny loops, but space-time itself still starts out smooth. Loop quantum gravity makes a sharper move. It suggests that the fabric is not a fabric at all. The geometry of space is built from discrete quanta, and continuity is an illusion that only appears when you stand far enough back. To appreciate how radical this is, remember what general relativity says. At its core, Einstein's theory does not treat gravity as a force that pulls on objects in space. It says that what we call gravity is really the curvature of space-time itself. The geometry is encoded in a mathematical object that tells you how rods and clocks behave, how straight lines bend, how volumes and areas are measured. In classical relativity, that geometry can vary smoothly from point to point without any smallest step. You can zoom in forever and always talk about smaller regions with slightly different curvature. Loop quantum gravity begins by refusing to take that smoothness for granted. If everything else in nature turns out to be quantized, from energy levels in atoms to angular momentum and electric charge, why should geometry itself be exempt? The idea is to take the same quantum logic that we applied to matter fields and aim it at the variables that describe space-time. Instead of treating the gravitational field as a continuous surface, you treat it as something that can exist only in discrete states. The technical route into this is twisted, but the picture it leads to is surprisingly visual. One of the first steps is to rewrite general relativity in a language that looks more like a gauge theory, similar to the ones used for the other forces. In that form, you can build objects that capture how geometry is twisted along loops in space, rather than at isolated points. These loop-based quantities turn out to be well suited to quantization. From them emerges the name loop quantum gravity. When you quantize these loops, the classical picture of a smooth field is replaced by a network of links and nodes. This structure is called a spin network. Imagine a web of lines meeting at junctions, like a strange three-dimensional spiderweb that fills space. Each line carries a quantum number that represents a chunk of area. Each node represents a chunk of volume. The network is not laid out inside space. In a very real sense, the network is space. The distances and angles you experience arise from the relationships between the nodes and links. In this framework, geometric quantities that were once continuous become operators with discrete spectra. That sentence sounds abstract, but the physical meaning is striking. If you measure the area of a surface in loop quantum gravity, you do not get a continuum of possible values. You get a sum over contributions from the links that pierce that surface, with each link contributing a fixed chunk. There is a smallest non-zero area on the order of the Planck length squared. Similarly, the volume of a region is built from contributions at the nodes inside it, leading to a smallest non-zero volume on the order of the Planck length cubed. This is the atomization of geometry. Just as you cannot have half an electron, you cannot have an area smaller than the smallest quantum of area. Of course, you can still have large areas and volumes by adding many quanta together. A mountain, a room, your own body, all correspond to enormous numbers of these microscopic geometric units. On those scales, the granularity is completely invisible. in the same way that the graininess of matter is invisible when you look at a glass of water rather than its molecules. A useful mental picture is to think of a digital image. Up close, you can see individual pixels, each with a single colour. From a distance, your brain blurs those pixels into smooth gradients and curves. In loop quantum gravity, the spin network is the pixel grid of space. The Planck length sets the pixel spacing. At human scales, the pixels are so tiny and numerous that straight lines and smooth surfaces are excellent approximations. At the Planck scale, the grid structure dominates. There is no meaning to distances smaller than the spacing of the network, because there are no nodes or links to support such distances. One of the key challenges for any theory like this is to show how the familiar smooth spacetime of general relativity emerges when you average over many quanta. Loop quantum gravity tackles this through coarse graining techniques and semi-classical states. You build spin networks with an enormous number of nodes arranged in patterns that mimic a given classical geometry. In those states, the expectation values of area and volume operators match the predictions of general relativity, up to tiny corrections suppressed by powers of the Planck length. The smooth fabric appears as a collective behaviour of countless discrete bits of geometry. So far we have talked mostly about space, a snapshot of the universe at an instant, but relativity insists that space and time are woven together. Loop quantum gravity extends the spin network picture into the time direction by letting the network evolve. Links and nodes can split, merge, and rearrange. The history of this evolution is called a spin foam, a kind of four-dimensional network of faces, edges, and vertices. If a spin network is the skeleton of space, a spin foam is the skeleton of space-time. Events correspond to changes in the connectivity and labels of this underlying graph. This dynamic view has powerful implications for some of the most puzzling places in physics. Take the Big Bang. In classical general relativity, if you run the universe backward in time, the scale factor shrinks towards zero, densities and curvatures blow up, and you hit a singularity where the equations lose meaning. In loop quantum cosmology, which applies the tools of loop quantum gravity to simplified models of the universe, that singularity is replaced by a bounce. As the density approaches the Planck scale, the discrete nature of geometry generates an effective repulsion that halts the collapse and reverses it. Before our expanding phase, there may have been a contracting phase. A similar story plays out in models of black holes. Classical relativity predicts that deep inside, beyond the event horizon, curvature grows without bound at a singular point or ring. In loop-based models, the quantization of area and volume again tempers this divergence. The geometry cannot shrink into nothing once you reach the smallest units. Instead, the core of the black hole is replaced by a region of extremely high but finite curvature, possibly connecting to another branch of space-time. These are still active research areas, not settled facts, but they show how discrete geometry can soften the infinities that signal the breakdown of classical theory. Loop quantum gravity also carries a philosophical weight. It is built to respect background independence, the idea that there is no fixed stage on which physics plays out. The network of loops does not live in a pre-existing space. It defines space. This is in contrast to many quantum field theories, which start by assuming a fixed background and then quantize fields on top of it. In loop quantum gravity, the background is not something you can specify. It is something that emerges from the quantum state of geometry itself. Of course, this approach has its own challenges. Constructing states that look exactly like the world we see, with its particular matter fields and cosmological history, is difficult. Making sharp contact with experiments is even harder. Just like string theory, loop quantum gravity operates at scales that are far beyond our direct reach. Its predictions often reduce to tiny corrections to general relativity or quantum field theory, hard to detect amid noise. There is ongoing work on possible observable signatures in cosmological data or in the detailed behaviour of black holes, but nothing conclusive yet. For our story, the important thing is that loop quantum gravity offers a concrete image of what it might mean for space itself to be quantized. It turns the abstract Planck length into a literal minimal grain of area and volume, encoded in the edges and nodes of spin networks. It replaces the smooth manifold of Einstein with a combinatorial structure that has no distances smaller than its own links. In the next part, we will step back from the technical details and ask a more general question. Whatever the correct theory turns out to be, what does space-time probably look like right at the Planck scale? We will dive into the idea of quantum foam, where micro-black holes, worm-like connections and violent fluctuations blur the very meaning of distance. By now we have looked at two very different blueprints for quantum gravity: strings that vibrate at the Planck length, loops that turn geometry into a network of discrete chunks. In both stories there is a common message. The smooth space-time of Einstein cannot survive unchanged all the way down. At the Planck scale, something violent and unfamiliar must be happening. Even without committing to any one theory, we can sketch a picture of what space-time probably looks like when you zoom in far beyond atoms and even far beyond quarks. The usual name for that picture is quantum foam. Quantum foam is a phrase coined to capture a simple but unnerving idea. On large scales, space-time looks like a calm ocean, gently curved by stars and galaxies. On tiny scales, that same ocean should be whipped into a froth of waves, bubbles, and whirlpools. The geometry itself jitters and fluctuates, driven by the same quantum uncertainty that makes particles behave like waves. Instead of a single definite shape for space and time, there is a restless superposition of wildly different shapes. Why would space-time misbehave so badly? Remember the uncertainty principle. If you try to confine energy to a very small region, you pay a price in fluctuations. Even vacuum is not truly empty. Particle pairs flicker into existence and vanish again, borrowing energy from nothing for very short times. At everyday scales, these vacuum jitters only show up as tiny corrections. At the Planck scale, their gravitational effects can no longer be ignored. The energy density in a tiny patch of vacuum becomes large enough that space-time around it curves strongly. Instead of a calm background, you get a roiling mess of curvature. In this stormy regime, the distinction between different kinds of structures begins to blur. A little bump in curvature that would be a mild ripple at large scales can, at Planck-sized distances, look like a miniature black hole. A fluctuation in the gravitational field can briefly create a region where light cones tip over, trapping light and then releasing it as the fluctuation fades. These micro-black holes would form and evaporate in times on the order of the Planck time, far too quickly to be seen as ordinary objects, but important enough to change the meaning of distance. You can think of these micro-black holes as the gravitational analogue of virtual particles in quantum field theory. Virtual particles are not directly observed as isolated things, but their presence is felt in the forces between charged particles and in subtle shifts of atomic energy levels. In a similar way, a sea of virtual micro-black holes and worm-like defects in spacetime could leave fingerprints in how fields propagate, even if we never catch one in the act. The phrase worm-like defects hints at another layer of weirdness. In classical general relativity, it is possible to have solutions where spacetime connects distant regions through narrow tunnels called wormholes. These are exotic and unstable in most realistic settings. At the Planck scale, however, the enormous fluctuations of geometry may constantly create and destroy tiny wormholes, linking points that are classically far apart. The topology of space, meaning the way it is connected, is no longer fixed. It churns along with the metric. Imagine trying to draw a straight line between 2 points through this roiling foam. At macroscopic scales, you can define a geodesic, a path that minimizes distance. At Planck scales, the very notion of a single smooth path breaks down. The line you try to draw is shredded into many possible routes, some looping through temporary tunnels in the foam, others skirting around micro-horizons. The idea of the shortest distance becomes fuzzy because the background it depends on is not stable. This fuzziness has deep implications for a concept we usually take for granted in physics: symmetry. Many of our most cherished conservation laws and regularities, like energy conservation and the constancy of the speed of light, are tied to symmetries of space-time. If space-time is perfectly uniform and looks the same in every direction, certain quantities are conserved. If it is smooth and respects Lorentz invariance, meaning the laws of physics look the same in any inertial frame, then there is a universal speed limit and a clean notion of causal structure. So what happens if the fabric that supports these symmetries dissolves into foam at the Planck scale? One possibility is that the symmetries are exact only at larger scales, where the foam has been averaged out and break down slightly in the deep ultraviolet. That would mean tiny violations of Lorentz invariance or subtle energy non-conservation at extreme energies. Another possibility is more subtle. Even though the microscopic structure is discrete and wildly fluctuating, the symmetries may re-emerge statistically, the way smooth behaviour emerges from atoms in a fluid. In that case, the foam would be like grains of sand in a glass window, invisible to light with wavelengths much larger than the grain size. Different approaches to quantum gravity take different positions on this. Some versions of loop-based theories treat the discreteness of geometry as fundamental and explore how symmetry is recovered approximately at larger scales. Certain string-inspired pictures, especially those with holographic dualities, suggest that exact Lorentz invariance might survive all the way down, with the foaminess expressed in more abstract variables. Observationally, we can actually test some of these ideas by looking for energy-dependent speeds of light over cosmic distances. So far, very tight bounds suggest that if there is any violation, it is extremely small. There is another way to appreciate the weirdness of quantum foam, and it connects back to a simple question. What is a particle? In everyday quantum field theory, a particle is a ripple in a field defined on a fixed spacetime. In a foamy spacetime, the field itself has to ride on a background that is flickering and changing. A wave packet that starts out as a neat bump in a calm region of space may get scrambled by the shifting geometry. In the most extreme regime, the distinction between a ripple of a field and a ripple of spacetime itself may dissolve. A micro-black hole could just be a particularly intense excitation of gravity, and particles travelling through the foam may continuously exchange identity with geometric excitations. This blending of matter and geometry is a hint of what a truly unified description might look like. At large scales, we draw a clean line. Here are particles moving, here is the spacetime they move through. At the Planck scale, that division is probably artificial. There are only quantum degrees of freedom that sometimes look like fields in space, and sometimes like space itself, depending on how you zoom out and which questions you ask. For us, living on human scales, all of this is hidden behind a thick layer of averaging. The photons that reach your eye from a star have travelled through vast stretches of space. Any tiny distortions from Planck's scale foam along the way are smoothed out. The paths we compute using general relativity are like averaged highways laid over a rough microscopic terrain. The fact that we can treat spacetime as smooth and talk about definite distances is not proof that it is truly continuous. It only means that the foam is too fine-grained for our current experiments to feel. Yet the foam matters in a crucial way when we talk about the beginning of the universe and the interiors of black holes. In those regimes, curvatures and densities approach Planck scales. The classical description predicts singularities where quantities become infinite and time seems to end. Quantum foam offers a different picture. Instead of a point where the laws break, there is a regime where the classical notion of distance, time, and even causal order simply stops being the right language. The foam may smooth out the singularity, replacing it with a region of extreme but finite density and wild topology. In the next part, we will push this idea to its logical conclusion. We will wind the clock all the way back to the earliest moments of the cosmos, when the entire observable universe was compressed into a region smaller than an atom, and ask what it means to talk about a Big Bang in a world where spacetime itself is made of quantum foam. Picture the universe as it is now, full of galaxies drifting apart. Then imagine hitting reverse on the whole thing. Galaxies draw closer together, clusters tighten, the cosmic web folds in on itself. Stars that were once separated by light years move into crowded neighbourhoods, until eventually there are no separate galaxies or stars at all, just an almost uniform fireball. Keep running the film backward and that fireball grows denser and hotter, its ingredients squeezed into a smaller and smaller region. At some point, long before atoms or even protons can exist, the entire observable universe fits into a volume smaller than a single atomic nucleus. Push further still, and all those distances approach the Planck length. That earlier stage is what we call the Planck epoch, and it is the edge of our current understanding. Cosmology lets us track this rewind quite far with real physics. Today the universe is about many billions of years old. A few 100,000 years after the hot beginning, matter and light decoupled, and the cosmic microwave background was released, a faint afterglow we can still observe. Before that, the universe was a plasma of nuclei and electrons. A few minutes after the beginning, nuclear reactions forged the first light elements such as helium and traces of lithium in a process called primordial nucleosynthesis. Earlier still, when the universe was less than a second old, it was a seething soup of fundamental particles, neutrinos streaming freely, quarks and gluons still tightly confined inside protons and neutrons, or maybe roaming in a quark-gluon plasma. These stages, as exotic as they sound, are described quite well by standard physics. General relativity handles the overall expansion. The standard model of particle physics handles the particle interactions. We test this combination by comparing its predictions with the abundances of light elements, the detailed pattern of ripples in the cosmic microwave background, and the distribution of galaxies today. The agreement is remarkably good. For a surprisingly long stretch of early time, our familiar theories seem to know what they're doing. But as we keep rolling back toward time zero, something starts to creak. Temperatures rise to energies where all the forces except gravity begin to merge in unified descriptions. Densities climb toward the Planck density. Curvatures of space-time grow enormous. Mathematically, if you follow the equations of classical general relativity all the way back, the scale factor that measures the size of the universe shrinks towards zero in a finite amount of time. Densities and curvatures shoot to infinity. That is the classical Big Bang singularity. A singularity is really a confession. It is the equation's way of saying this description no longer makes sense here. Infinite density and infinite curvature are not physical conditions you can realize. They are signals that some crucial piece of physics is missing. For the Big Bang, that missing piece is almost certainly quantum gravity. As the universe is compressed into volumes approaching the Planck scale, quantum fluctuations of space-time can no longer be treated as small corrections. The smooth fabric assumed by general relativity has been pushed past its breaking point. To get a feeling for how extreme the Planck epoch is, imagine compressing the entire observable universe into a region smaller than an atom, then shrink it further by many orders of magnitude until its radius is around the Planck length. Time intervals are equally extreme. The Planck time is roughly the time light needs to cross that tiny length, on the order of 10 to the minus 44 seconds. At earlier times than that, the very notion of a smooth ticking clock tied to space-time becomes suspect. You cannot just tack on a label that says earlier than 10 to the minus 44 seconds and pretend nothing has changed. So what, if anything, does it mean to talk about the universe at times earlier than the Planck time? There are several possibilities, and right now we do not know which, if any, is correct. In some scenarios inspired by loop quantum gravity, the classical singularity is replaced by a bounce. A previous contracting universe reaches Planck scale densities, quantum geometry effects create an effective repulsion, and the universe rebounds into an expanding phase. In that picture, our Big Bang is a transition rather than an absolute beginning. In some string-inspired scenarios, the universe undergoes phases where extra dimensions grow and shrink, or where branes collide and separate in a higher dimensional space. The hot Big Bang we see is a late chapter in a much longer story. There are models where time extends infinitely into the past, others where time itself emerges in a more subtle way from an underlying timeless quantum state. There is even the possibility that asking what happened before the Planck epoch is like asking what is north of the North Pole, a question that sounds meaningful in everyday language but breaks down once you see the full geometry. What all of these ideas share is recognition that near the Planck epoch, our usual language of space expanding and time flowing may not apply in the ordinary sense. If space-time is made of quantum degrees of freedom, then the early universe might be better described as being in some highly excited state of that underlying system. The smooth expanding space-time we talk about in cosmology emerges only after those degrees of freedom settle into a particular phase. Before that, there may be no clear separation between space, time, and matter. This is hard to picture because every intuition you have was built in a world where space-time is already classical. Your brain expects events to line up along a time axis with a well-defined before and after. At the Planck epoch, that ordering might itself be a coarse-grained description. Different branches of geometry, different topologies, might coexist in a quantum superposition. Asking which one really happened could be as misguided as asking where exactly an electron was before you measured it. Despite this conceptual fog, the Planck epoch is not beyond all influence. Its physics can leave imprints on later eras through processes like cosmic inflation. If a brief period of accelerated expansion occurred very early on, it could stretch quantum fluctuations from sub-Planckian scales to astronomical sizes, freezing them in as seeds for the large-scale structures we see today. In that way, tiny jitters in whatever pre-geometric state existed at the Planck epoch could be echoed in the distribution of galaxies and in the pattern of temperature variations in the cosmic microwave background. However, this connection comes with a catch. The so-called trans-Planckian problem reminds us that we are extrapolating our equations into a regime where they are not trustworthy. When we trace a mode in the cosmic microwave background backward in time, its wavelength shrinks, and if inflation lasts long enough, that wavelength eventually becomes shorter than the Planck length. At that point, we're using a description of quantum fields on a smooth spacetime, in a domain where spacetime itself should be foam-like and quantum. Some researchers look for subtle signatures of this mismatch in the data. Others hope that a complete theory will show that the final predictions are insensitive to the details of the Planck era. For now, the Planck epoch remains a kind of cosmic horizon in theory space. On this side of it, we have a well-tested hot Big Bang model that successfully explains a wide range of observations. On the other side lies speculation, guided by mathematical consistency and by hints from candidate theories of quantum gravity, but not yet anchored by direct evidence. The fact that we can even articulate the question of what the universe was like at 10 to the minus 44 seconds is already astonishing. We are creatures made of atoms living on a mid-sized planet who have managed to infer that there is a limit to how far back our current laws can see. In the next part, we will follow one of the most powerful bridges from that mysterious epoch to the cosmos we observe today. We will explore how tiny quantum fluctuations, born when the universe was unimaginably small, may have been stretched by inflation into the seeds of galaxies, clusters, and the vast cosmic web, connecting Planck-scale physics to the largest structures in the universe. Stand outside on a clear night and look up. The sky feels calm. Stars are scattered in a pattern that does not seem rushed. Galaxies drift apart at a stately pace. Nothing about that quiet scene screams that, in its first instant, the universe may have expanded faster than you can really imagine, taking distances smaller than atoms and blowing them up to scales larger than galaxy clusters in a blink. Yet that is what inflation proposes, and it is the bridge between Planck-scale jitter and the vast cosmic web above your head. Inflation is the idea that very early on, for a brief period, the universe did not just expand. Its expansion rate itself exploded. Space doubled in size again and again in an extremely short time. This burst smooths out almost any initial mess. Distant regions come to share the same conditions and temperatures. Curvature is ironed out so thoroughly that billions of years later the universe still looks astonishingly flat on large scales. Without inflation, we are left with puzzles that feel almost like cosmic coincidences. With it, those coincidences become natural consequences of a violent but simple early phase. The horizon problem is one of those puzzles. When we look at the cosmic microwave background, the afterglow from when the universe was only a few 100,000 years old, we see that it has almost the same temperature in every direction. Regions on opposite sides of the sky were never in contact in the simple, hot Big Bang picture. Light did not have enough time to cross between them and share information. Yet they look coordinated, as if someone carefully matched their thermostats. Inflation fixes this by making the observable universe a small patch of a region that was once in close causal contact, then stretched far apart. The flatness problem is another. General relativity allows universes with different curvatures. Some are positively curved, like the surface of a sphere. Others are negatively curved, like a saddle. A perfectly flat universe is a very specific case that is unstable in simple models. A tiny deviation early on would grow over time, producing either a rapid recollapse or a wildly open geometry. Observations show that our universe is extremely close to flat today, which means it must have been absurdly close to flat in its youth. Inflation solves this the way a balloon solves wrinkles. Exponential expansion blows up any initial curvature, making space appear flat over regions as large as we can see. So inflation gives us a neat solution to large-scale puzzles. Where does the Planck scale come into the story? Through the tiny imperfections that inflation refuses to smooth out. Even in a rapidly expanding universe, quantum fields are never perfectly quiet. They fluctuate. A field that drives inflation, often called the inflaton in these models, jitters slightly in value from point to point because quantum mechanics will not allow it to settle everywhere in the exact same state. Imagine that field as a landscape of energy density filling space. Quantum fluctuations create tiny hills and valleys in that landscape. During inflation, space is expanding so fast that these little wrinkles get frozen in. Regions that were once in close contact are ripped apart faster than signals can even up their differences. A fluctuation that started at subatomic scales is dragged out until its imprint spans light years, then millions of light years. The wrinkles become permanent variations in the density of matter and radiation. After inflation ends, the universe reheats and settles back into the more sedate hot Big Bang expansion. Those tiny differences in density are still there, encoded in the distribution of matter. Slightly overdense regions pull in more matter under gravity and grow into the seeds of galaxies and clusters. Slightly underdense regions are left as the gaps between cosmic structures. In this way, quantum noise at unimaginably small scales becomes the architect of the largest patterns in the universe. We see direct evidence of this process in the cosmic microwave background. That faint microwave glow is not perfectly smooth. It has tiny temperature variations at the level of a few parts in 100,000. When you map those variations across the sky, you find a particular pattern of hot and cold spots, with a characteristic range of sizes. That pattern matches what you would expect from quantum fluctuations stretched by inflation, then allowed to evolve under gravity and simple physics of radiation and matter. Even more impressively, the statistics of those fluctuations are almost scale invariant. That means the strength of the variations is nearly the same across a wide range of sizes, with only a gentle tilt. This is exactly the kind of spectrum inflation tends to produce. It is as if the universe is whispering to us that, yes, its large-scale structure really did begin as quantum ripples in a nearly de Sitter-like expansion phase. There is a further possible signature that physicists have hunted with particular excitement. If inflation involved huge energies near the grand unification scale, then gravitational waves would also be created by quantum fluctuations. These primordial gravitational waves would leave a distinct imprint on the polarization pattern of the cosmic microwave background. Specifically, they would create a swirl-like pattern known as B-mode polarization. Detecting a primordial B-mode signal would be like hearing the faint rumble of the universe stretching at its birth. Experiments have reported hints, and then had to step back as dust and other foregrounds mimicked the desired pattern. The hunt continues with ever more sensitive instruments. A clean detection would give us a direct window on physics at energy scales, far beyond any accelerator we can build on Earth, possibly approaching the scales where quantum gravity effects become important. All of this makes inflation one of the most successful and tantalizing ideas in cosmology. It connects deeply quantum processes to the arrangement of galaxies over tens of billions of light years. At the same time, it opens a subtle wound in our theoretical confidence, the trans-Planckian problem. To understand that, imagine taking one of the modes in the cosmic microwave background that corresponds to a particular size on the sky. You can track that mode backward in time through the equations of inflation. As you do, its physical wavelength shrinks. If inflation lasted long enough before the mode exited the horizon during the rapid expansion, then earlier in its history that wavelength could have been shorter than the Planck length. Yet our whole description of that mode assumes it is a simple ripple of a quantum field on a smooth spacetime. Below the Planck scale, we do not expect spacetime to be smooth. We do not trust ordinary quantum field theory. We are using a tool outside its domain and hoping the final answer is still reliable. Many analyses suggest that reasonable changes in the physics at ultra-short distances do not dramatically change the predictions for observable structures. In that case, the Planck scale details are blurred by the inflationary process, and our ignorance is forgiven. Still, the issue remains as a conceptual tension. Inflation almost begs for a deeper theory that can describe how quantum fluctuations behave when their wavelengths are shorter than the fundamental grain of spacetime. Whether that theory looks more like strings, loops, or something entirely different, it would complete the story inflation began, connecting the foam of Planck-scale geometry to the cosmic tapestry of galaxies and voids. In the next part, we will leave the early universe and turn the cosmos into a laboratory, using distant explosions and precise measurements to ask whether any trace of spacetime granularity shows up in the way light and particles travel across the vast distances between galaxies. We have spent a lot of time imagining experiments that no human civilization could ever realistically build. Colliders the size of galaxies, detectors that can poke directly at the Planck length. Nature looks at these plans and calmly says that it has already done something better. It has been running ultra-high energy experiments for billions of years, across distances so vast that no engineer could dream of them. The universe is not only the thing we want to understand, it is also the only laboratory capable of amplifying tiny Planck scale effects into something we might actually measure. The basic idea is simple and powerful. If space-time has a microscopic grain or foaminess, it might slightly change the way particles and light propagate. That change could be so tiny at human scales that it is hopeless to detect in the lab. But stretch the journey to billions of light years, and even a minuscule effect might accumulate into something real. A small delay per meter can grow into a measurable lag if the signal travels across a meaningful fraction of the observable universe. One of the cleanest places to look is in the speed of light itself. In Einstein's relativity, the speed of light in vacuum is a true constant. It does not care about the energy of the photon, the color of the light, or the direction it travels. If space-time is perfectly smooth and Lorentz symmetry is exact, that statement holds at all scales. Many quantum gravity ideas, however, predict that at extremely high energies this picture might need a tiny correction. The speed of a photon could depend ever so slightly on its energy, with higher energy photons moving a hair faster or slower than low energy ones. We cannot test that by timing a flashlight across your living room. The effect, if it exists, would be far below our ability to measure over such small distances, so we let the cosmos do the heavy lifting. Distant astrophysical explosions such as gamma-ray bursts send out flashes of photons covering a wide range of energies. These flashes travel for billions of years before they reach our detectors. If high-energy photons and low-energy photons do not travel at exactly the same speed, they should arrive at Earth with a slight spread in their arrival times, even if they were emitted together. Gamma-ray bursts are almost ideal for this test. They are some of the brightest explosions in the universe, likely tied to collapsing stars or merging neutron stars. Their light curves show sharp spikes and substructure on very short timescales. Imagine a distant burst sending out a crisp pulse that includes both relatively soft gamma rays and very hard ones. If space-time granularity changes the travel speed by even 1 part in 100 million trillion, the difference can add up over cosmological distances to milliseconds or more. Modern space telescopes can easily resolve such tiny differences in timing. Astronomers have combed through data from many bursts, looking for systematic energy-dependent delays that increase with distance. They find some lags, but these often match what you would expect from processes at the source. High-energy photons can be produced in slightly different regions or at slightly different times than low-energy ones. When you correct for that as best you can, the sky sends a clear message. If there is any quantum gravity-induced energy dependence in the speed of light, it must be extremely small. Many naive models that predicted large effects at the Planck scale are already ruled out. This is instructive. It does not mean space-time is perfectly smooth in a naive way. It means that if there is foam, it respects Lorentz symmetry to a very high degree, or hides its effects through more subtle mechanisms. The fabric can be grainy without acting like a crystal that picks out preferred directions or energies. Think of air molecules. At the microscopic level, the gas is a swarm of bouncing particles, yet sound waves travel through it at a well-defined speed that does not care about the tiny details of the motion as long as you stay in the right regime. Gamma-ray bursts are not the only tools in this cosmic lab. We can also use flares from active galactic nuclei, the cores of galaxies where supermassive black holes feed on infalling matter and launch jets of high-energy particles. These jets shine in gamma rays and change brightness on relatively short timescales. Once again, we can compare the arrival times of photons at different energies and set limits on any possible dispersion caused by space-time structure. High-energy cosmic rays give us another handle. These are particles, mostly protons or nuclei, that slam into our atmosphere with energies far beyond what any human collider has reached. Their existence raises interesting questions, because interactions with the diffuse background of low-energy photons that fills the universe should sap their energy over long distances. If quantum gravity modifies the rules that govern these interactions, it could either suppress or enhance certain reaction channels. By studying the spectrum and arrival directions of the highest energy cosmic rays, we can test whether the kinematic rules of special relativity hold up even under such extreme conditions. In all of these cases, the pattern so far is the same. Observations keep coming back with answers that say the familiar symmetries of space-time are intact to the level we can currently probe. Light speed is constant to astonishing precision. Thresholds for particle reactions behave as expected. If quantum gravity introduces tiny violations, they are smaller than the bounds we have set using explosions and collisions that the universe so kindly provides. There is an almost playful twist to this story. To test theories about the tiniest scales, we rely on the largest structures and the most distant events. A gamma ray burst on the far side of the cosmos becomes a probe of Planck-scale physics. A high-energy neutrino that has travelled unimpeded through entire galaxies becomes a messenger from regimes of density and temperature we can barely describe. The sky above us turns into something like a gigantic interferometer and clock, with baselines measured in billions of light years. Gravitational waves add a newer piece to the toolkit. These ripples in spacetime, first directly observed from merging black holes, also travel vast distances. If the granularity of spacetime affected different frequencies of gravitational waves differently, we might see distortions in the observed waveforms compared to what general relativity predicts. Current observations are not yet sensitive enough to pick up Planck scale effects this way, but future detectors with longer baselines and greater precision could turn gravitational wave astronomy into another test of quantum gravity. All of this has a philosophical bite. It tells us that the Planck scale is not entirely sealed off behind an impenetrable barrier. Even though we cannot build an instrument that directly images lengths of 10 to the minus 35 meters, we can ask nature whether its microscopic quirks leak into the propagation of light and particles over cosmic distances. So far, the answer seems to be that nature is extremely good at hiding those quirks, or that our guesses about how they should show up have been naive. For the theories, this is both guidance and constraint. Any model of quantum gravity that predicts large violations of Lorentz symmetry or strong energy-dependent dispersion is in trouble. The universe has already said no. More subtle ideas, where spacetime is discrete yet respects the familiar symmetries in an emergent way, remain viable. In that sense, high-energy astrophysics and quantum gravity are no longer separate stories. They are chapters of one investigation, where observations of distant cataclysms narrow the menu of possible microscopic worlds. In the next part, we will turn our attention back to Earth and survey the experiments that push at the boundaries from below, using colliders, neutrino beams, dark matter searches, and precision measurements of gravity to look for tiny deviations that might be the first whispered hints of Planck-scale physics in our own backyard. So far, our search for Planck-scale fingerprints has mostly looked outward, to violent events scattered across the universe. Now we turn inward, to laboratories on Earth where humans are quietly trying to coax the smallest possible hints of new physics out of carefully controlled experiments. At first glance, these machines live unimaginably far below the Planck energy. Even our most powerful colliders are not close, yet precision has a superpower. If the Planck scale changes the rules even a little, those changes can ripple downward as tiny corrections that extremely careful measurements can see. Start with the most iconic of these machines, the large circular colliders that fling protons around at nearly the speed of light and smash them together. When protons collide at trillions of electron volts, the collision energy briefly concentrates into a minuscule region. Quantum fields roar to life, spitting out showers of new particles. Detectors surrounding the collision points record the tracks and energies of the debris, and from that wreckage physicists reconstruct what must have happened in the first instant after impact. In principle, if there were new heavy particles whose mass is not too much higher than the collision energy, they could appear as bumps in the distribution of events, or as strange combinations of decay products. Many theories inspired by quantum gravity ideas predict such particles: supersymmetric partners of known particles, heavy cousins of the graviton that betray extra dimensions, exotic resonances that hint at new fields in the early universe. Decades of collider data have put strong limits on many of these possibilities. The absence of clear signals is itself a message. If quantum gravity leaves imprints in the particle spectrum, it hides them at energies higher than we have yet reached, or dresses them in subtler clothes. But colliders do more than hunt for obvious new peaks. They also test the standard model to absurd accuracy. When you measure how often certain processes occur, or how particles like the Higgs boson decay, you compare those numbers against predictions that include quantum corrections from every known field. A tiny mismatch, repeated consistently across channels, can hint that something else is running in the loops. In this way, Planck-scale physics could show up as a tiny deviation in a scattering rate, even if we never produce the heavy states directly. One famous example sits in the magnetic behavior of the muon, a heavier cousin of the electron. The way a muon wobbles in a magnetic field can be predicted from the Standard Model with stunning precision. Experiments have measured that wobble at high accuracy, and for years there has been a tension between theory and measurement. It is not yet clear whether this is a definite sign of new physics or a subtle issue in the calculations, but it shows the strategy. You do not always need raw energy to push the frontier. You can also amplify sensitivity by comparing theory and experiment to many decimal places and seeing where reality refuses to line up perfectly. Neutrinos give us another path. These ghostly particles barely interact with matter, which makes them maddening to detect but wonderful messengers from extreme environments. They are also sensitive to new physics because their masses are tiny, and their behavior is governed by delicate interference effects as they oscillate between different types during flight. Long baseline experiments send beams of neutrinos through hundreds of kilometers of rock, measuring how their flavors change along the way. Any tiny modification in the way neutrinos propagate through space-time, perhaps from quantum gravity-induced violations of Lorentz symmetry, could show up as an unexpected twist in the oscillation pattern. So far, oscillation experiments fit neatly into a picture where neutrinos have small but non-zero masses and mix according to a three-flavor framework. Yet they remain a playground for possibilities. Some models of quantum gravity predict energy-dependent effects that grow with distance traveled. In those scenarios, extremely long baseline neutrino observations, including those that use neutrinos from supernovae or distant cosmic accelerators, can set strong limits. Once again, the universe and our instruments cooperate. The cosmos provides the distance. Our detectors provide the timing and flavor resolution. Dark matter experiments add a different piece. We know from cosmic observations that most of the matter in the universe is invisible to light and does not fit into the Standard Model. Some candidates for dark matter, like certain weakly interacting massive particles, could also be tied to deeper unification schemes that connect to gravity at high energies. In deep underground laboratories, massive detectors filled with ultra-pure materials wait for an occasional dark matter particle to strike a nucleus and produce a tiny flash of light or a faint vibration. These detectors are masterpieces of patience and cleanliness. They are shielded from cosmic rays by mountains or kilometers of rock. Every background source of noise is tracked and reduced. Years can pass without a single convincing candidate event. That slowness is part of their power. If Planck scale physics leaves behind a relic particle that makes up dark matter, and if that relic has even the slightest chance of colliding with ordinary matter, these experiments will eventually hear it. If they do not, entire classes of models get squeezed or ruled out, forcing our ideas about high-energy unification to evolve. At the opposite end of the size spectrum sit tabletop experiments that measure gravity itself with exquisite precision at short distances. Newton's law works beautifully for planets and apples, but what about separations of a fraction of a millimeter or less? Some theories with extra dimensions predict that gravity could deviate from the simple inverse square law at these scales, as gravitational field lines leak into hidden directions. By carefully measuring the torque between tiny masses suspended on torsion balances, or by watching how small test objects respond to oscillating attractors, researchers can probe for such deviations. So far, gravity has been boring in the most reassuring way. The measured force matches the predictions of general relativity and Newtonian approximations down to very small distances, with no sign of extra dimensions opening up. Each null result, however, slices away a region of theory space, telling us that if extra dimensions exist, they must either be smaller than a certain size or affect gravity in more subtle ways than the simplest pictures suggest. Then there are experiments that bridge quantum mechanics and gravity more directly. Proposals exist to place increasingly massive objects into quantum superpositions of different locations and then let them interact gravitationally. If the gravitational field can carry quantum information, the resulting entanglement patterns between those objects might reveal it. These are early days for such ideas, and the experiments are technically daunting, but they embody a new attitude. Instead of treating gravity as too weak to see at small scales, we use the extreme sensitivity of quantum systems as amplifiers of its effects. Atomic clocks and interferometers also join the quiet revolution. By comparing the ticking of different clocks at different heights in Earth's gravitational field, we have tested time dilation to incredible precision. atom interferometers send coherent matter waves along different paths and recombine them, creating fringes that are exquisitely sensitive to gravitational potentials and acceleration. While these setups are not yet poking the Planck scale, they provide ever more stringent tests of the equivalence principle and of the constancy of fundamental constants. Any Planck scale mechanism that trickles down into slight violations of these principles risks being exposed. What ties all of these efforts together is a kind of experimental humility and determination. No single collider run, no single neutrino beam, no single torsion balance will shout the secrets of quantum gravity at us. Instead, we gather constraints from many directions, each chipping away at what is possible. A tiny anomaly in one arena must line up with consistency in others. Theoretical ideas that once roamed freely across the chalkboard are now forced to thread a narrowing needle of observational and experimental facts. From the outside, this can look like a long series of non-detections. No new particle here, no violation there. But in the deeper story, every precise agreement with general relativity and the Standard Model is telling us something about how a Planck scale theory must behave when it descends to our world. It must reproduce the symmetries we see. It must hide its discreteness behind emergent continuity. It must leave only faint, carefully arranged fingerprints. In the next part, we will take one more conceptual leap. We will explore the idea that space and distance themselves might not be fundamental at all, but byproducts of quantum information and entanglement, with the Planck scale marking not just the smallest distance, but the smallest meaningful chunk of information out of which space-time is woven. Up to now, we have treated space as the thing everything else lives in. Even when we made it grainy or foamy, we still imagined it as the underlying stuff. Fields live on space, particles move through space, gravity curves space. There is a newer and stranger idea on the table. Maybe space is not the stage at all. Maybe space is what it looks like when something deeper organizes itself, the way temperature appears when molecules share energy. In this view, the Planck scale is not just a smallest distance. It is the size of the fundamental bits of information from which space-time is woven. The bridge to that idea comes from black holes. These objects have been troublemakers throughout our story. Classically, a black hole is a region from which nothing can escape, defined by its event horizon. For a long time, people thought of it as a simple dead end. Then quantum field theory and curved space-time stepped in. Hawking showed that black holes radiate, slowly losing mass. This radiation seems to carry no information about what fell in, threatening to destroy the principle that information is preserved in quantum mechanics. Trying to resolve that tension led to a powerful clue. When you calculate how much information a black hole could hold, you might expect the answer to scale with its volume. After all, more space inside should mean more room to hide stuff. Instead, the entropy of a black hole, which measures its information content, scales with the area of its horizon. Double the radius of the black hole and the area squares, while the volume grows even faster, yet the information tracks only the surface. It is as if the degrees of freedom live on the boundary, not in the interior. This is the seed of the holographic principle, the idea that in a theory including gravity, the maximum amount of information that can fit in a region is proportional to the area of its boundary measured in Planck units, not to its volume. One Planck area carries roughly 1 bit of information. That is an astonishing statement. It suggests that what we think of as a three-dimensional region of space may be fully described by data living on a lower dimensional surface that encloses it. In the same way, a two-dimensional hologram on glass can encode a three-dimensional image. Holography stopped being just a slogan when a concrete example appeared in the form of a duality between a gravitational theory in a space with negative curvature, called anti-de Sitter space, and a quantum field theory without gravity living on its boundary. On one side of the relation, you have strings and branes and curved geometry. On the other, you have ordinary-looking fields in flat space-time with no gravity at all. The claim is that every process in the bulk gravitational theory has a mirror description in the boundary field theory. One system, two radically different languages. You do not need to dive into the technical details to feel the shock. In this duality, the extra dimension of the bulk space is not an independent thing. It is encoded in the patterns of quantum entanglement and energy in the boundary theory. Change the boundary state and you change the bulk geometry. A wormhole in the bulk corresponds to a particular structure of entanglement between parts of the boundary. A black hole corresponds to a hot thermal state with many degrees of freedom excited. This hints at a deeper moral. Geometry and gravity may not be fundamental. They may be macroscopic expressions of how quantum information is arranged. Entanglement is the spooky correlation that lets two distant particles share a state, so that measuring one tells you something about the other. In many body systems, entanglement is not a rare curiosity. It is the basic glue that holds quantum phases of matter together. The emerging view is that entanglement might also be the glue that holds space-time together. One striking line of research shows this in toy models. Take a network of simple quantum systems, such as qubits, connected in a particular pattern. Define a state where nearby qubits are more entangled than distant ones in a carefully tuned way. When you compute how information flows through this network and how difficult it is to separate parts of it, you find that its structure can be described as a kind of emergent geometry. Distances in that geometry correspond to how many entangling links you must cut to separate regions. More entanglement means shorter, effective distance. In that picture, the Planck scale sets the basic grain of this information network. Each link carries a discrete chunk of entanglement. Each node can store only so much information. Smooth space, with its familiar distances and angles, appears when you coarse grain over many links and nodes, just as a smooth surface appears when you average over the atoms in a crystal. A curvature in space-time could correspond to a change in the pattern of entanglement. Gravity becomes less a force, and more a manifestation of how information is distributed. This perspective reshapes the black hole information puzzle. Instead of thinking of information as stored deep inside a classical geometry, you see the entire space-time and the black hole horizon as emergent from an underlying quantum state. As the black hole radiates, the entanglement structure reorganizes. The information is not lost. It is scrambled and re-expressed in the outgoing radiation. Holographic dualities give examples where you can track this process all the way through, at least in simplified settings, and see that unitarity, the preservation of quantum information, is maintained. There is an almost poetic inversion here. We began by treating space-time as the most solid thing in physics, the arena that everything else depends on. Now it starts to look like the most fragile, like the thin sheen of order that appears when countless microscopic quantum variables settle into certain patterns. At the Planck scale, those patterns break into individual strands of entanglement. Talking about a location or a distance shorter than that is like trying to talk about half a bit of information. The language no longer fits the system. This information first view also connects naturally to ideas about computation and complexity. Some researchers have suggested that the volume of certain regions in spacetime, such as the interior of a black hole, might be related to how complex the corresponding quantum state is, measured by the length of the shortest sequence of simple operations needed to build it. Under this lens, the growth of a black hole interior over time is not just a geometric oddity, it is the growth of computational complexity in the underlying quantum system. In laboratories, we see hints of this kind of emergent geometry in analog systems. Fluids flowing at high speeds can produce horizons for sound waves, mimicking some aspects of black holes. Condensed matter systems with many interacting electrons can be described using holographic models borrowed from gravitational dualities. In these cases, no one thinks the fluid literally contains a tiny universe with gravity inside. Instead, the duality is a powerful metaphor made precise by equations. It shows how geometry can arise from degrees of freedom that do not look geometric at all. For our story, the key message is that the Planck scale may not simply be a brick wall in distance. It may be the native pixel size of an information network from which spacetime emerges. The grain we encounter when we talk about smallest lengths could be the granularity of quantum information itself, measured in qubits and entanglement bonds rather than in meters. In the final part, we will pull these ideas back together. We will step away from equations and metaphors and ask what it means, in human terms, that creatures built from Planck-scale quantum information have learned to measure the pixel size of their own reality, and are now trying to decode the deeper operating system that makes space, time, matter, and information all facets of one structure. If you have stayed with this journey all the way from human height down to the Planck length, you have done something unusual. You have let your everyday sense of reality be dismantled piece by piece. Solid objects turned into mostly empty space. Particles stopped being tiny marbles and became clouds of probability. Space-time itself stopped being a smooth background and dissolved into strings, loops, foam, and patterns of information. Now, we are ready for the hardest part of all, stepping back and asking what kind of world could have all of these faces at once. One way to think about it is to imagine that we have been describing different sides of one hidden structure. In one story, particles are vibrations of tiny strings. In another, geometry is made of discrete loops. In another, space-time is an emergent effect of quantum entanglement. In all of them, the Planck scale sits at the bottom as a kind of universal pixel size. Each approach tries to answer the same question. How do you build a world where gravity and quantum mechanics are both true without one tearing the other apart? Whatever the final theory looks like, it must pass a series of tests that reality has already set. At large scales, it must give us a universe that obeys general relativity to exquisite precision. Planets must trace out orbits, light must bend around stars, gravitational waves must ripple through space exactly as we have measured. At small scales, it must reduce to quantum field theory with its particles and forces, its interference patterns and entanglement. It must give the standard model where it is already successful, and show us where that model is only an approximation. At the Planck scale itself, it cannot dodge the core conflict forever. It must explain why attempts to probe smaller distances create black holes. It must tame the infinities that appear when we naively quantize gravity. It must tell us what really happens at the centers of black holes and in the first instant of the universe, where classical space-time breaks down. That is a tall order. Yet the fact that we can list these requirements shows how much we have already learned without having the final answer. It is tempting to imagine a future where someone writes down a single neat equation and declares the job finished. A theory of everything sounds like a trophy you hang on the wall. The reality is likely to be stranger. A truly unified framework may not look like a single formula. It may look more like a web of dual descriptions, each one better suited to a different regime. Strings in one language, loops in another, entanglement networks in a third, all secretly the same structure seen from different angles. Holography has already given us a taste of that possibility. A quantum field theory without gravity on a boundary can fully describe a gravitational world in a higher dimensional bulk. Two wildly different stories turn out to be two ways of encoding the same physics. If such dualities are a hint rather than a special case, then our current theories may be like different projections of a higher dimensional object. No single projection shows the whole thing, but together they reveal a deeper unity. Where does that leave us as human beings trying to make sense of our place in this structure? It is easy to feel small when you hear that the universe contains more Planck-sized intervals across a single proton than there are protons across the observable cosmos. It is easy to feel lost when you learn that space-time itself might be an emergent pattern in an abstract space of quantum states. And yet, there is another way to see it. We are made of this stuff. Every neuron in your brain is arranged from atoms, which are built from fields, which are expressions of deeper quantum degrees of freedom that know about the Planck scale. The same constants that define the Planck length and Planck time also determine the strength of forces in your cells and the nuclear reactions in your sun. The universe has, somehow, configured part of itself into a system that can turn around and ask what its own pixel size is. There is something almost circular and beautiful about that. The Planck scale is defined using constants we measured in the lab. Those constants came from experiments with light, from watching falling objects, from studying thermal radiation. We used telescopes, clocks, and accelerators built by hands to infer properties of reality that those hands will never touch directly. In doing so, we closed a loop. Quantum matter assembled into observers that decode the rules governing quantum matter and space-time itself. Will we ever know the final form of those rules? No one can say. Our instruments have limits, and so do our brains. There may be aspects of a full theory that are hard to express in the metaphors we like, but history suggests that even partial glimpses can be powerful. Newton did not know about quantum mechanics, and still gave us a theory of gravity that worked for centuries. Maxwell did not know about quantum field theory, and still unified electricity and magnetism. Each time, a new framework did not erase the old one. It revealed where it fits inside a larger picture. The same is likely true for us. General relativity and quantum field theory are not mistakes waiting to be thrown away. They are the low-energy, large-scale, and small-scale faces of something deeper. A future theory of quantum gravity will not make them obsolete. It will show why they work so well where they do, and where they subtly break down. It will give us a map of how smooth space-time, quantum fields, and information-theoretic descriptions all grow out of one underlying structure. That structure, whatever we finally call it, will still have to tell a story that reaches all the way back to human experience. It will still have to explain why dropping a ball makes it fall, why atoms stick together to form solids, why time seems to flow in one direction, why the night sky has galaxies arranged in filaments and voids. It will have to show how meaning and consciousness can arise in a universe whose smallest ingredients have no built-in purpose. There is a quiet comfort in this. You do not need to picture the Planck scale in vivid detail to be part of it. Every breath you take, every thought you have, already relies on the fact that there is a smallest meaningful volume, a shortest meaningful time, a grain to the universe that keeps its laws from collapsing into infinities. Without that grain, matter would not be stable. Black holes would not radiate in a consistent way. The Big Bang would remain a singular nonsense point instead of a doorway into a knowable past. So when you think about the Planck length, you can treat it as more than an absurdly small number buried in a textbook. You can see it as the pixel pitch on the screen of reality, the basic information unit of a cosmos that stretches from quantum foam to galaxy clusters. We are not outside that screen looking in. We are patterns drawn on it, momentary arrangements of Planck-scale bits that have become aware enough to ask what those bits are. The search for a unified structure that includes quantum gravity is not just a technical project for specialists. It is the latest step in a long human habit of refusing to accept that the familiar surface is the whole story. Once we thought the Earth was the center of everything. Then we learned it was one planet among many, around an ordinary star, in a galaxy that is not special, in a universe that may not even be unique. Now, we're adding another twist. Even the space that contains all of that may not be fundamental. It might be a derived thing, a shadow of a deeper order written in the language of quanta and information. If that feels dizzying, that is all right. The universe is under no obligation to match the scale of our intuitions. What matters is that we have learned to build bridges from what we can see to what we cannot. From the swing of a pendulum to the curvature of space-time, from a glowing piece of metal to quantum discreteness, from the crackle of cosmic radiation to a flash of expansion in the first instant. Each bridge carries us a little closer to the source, and there, at the edge of what we currently know, sits the Planck scale. Not a wall that says stop, but a signpost that says beyond here, your old maps are lying. The work of the coming decades and perhaps centuries is to draw new maps that pass that signpost without falling apart. However that story unfolds, one thing is already true. We live in a universe whose deepest structure may be far stranger and more unified than our everyday senses suggest, and somehow, from within that structure, we have begun to understand that fact.